In this lesson, I am going to show you how to solve the Legendre ODE using power series method. The Legendre ODE is 1 minus x squared times y double prime minus 2x y prime plus lambda y is equal to 0. Before going into solving the Legendre ODE, I am going to explain how Legendre ODE appears when solving Laplace equation in spherical coordinates. This is the Laplace equation, and let's write it down using spherical coordinates. 1 over r squared del r squared del r psi plus 1 over r squared sin theta del theta sin theta del theta psi plus 1 over r squared sin squared theta del phi squared psi is equal to 0. Now let's think about a problem that psi is not dependent on phi, which means del phi of psi is equal to 0. In that case, this differential equation simplifies to del r squared del r psi plus 1 over sin theta del theta sin theta del theta psi, which is equal to 0. Using separation of variable, we can assume our psi function, which is a function of r and theta only, is a function of r only multiplied by function of theta only. And after plugging r times theta to this equation, we can get this equation 1 over r ddr r squared ddr r plus 1 over theta function times sin theta dd theta sin theta dd theta and theta function, which is equal to 0. Now this part is only a function of r, this part is only a function of theta, which means this can be written as some constant minus lambda and this can be written as some constant plus lambda, and their summation will be equal to 0. And theta differential equation becomes 1 over sin theta dd theta sin theta dd theta and our theta function, which is equal to minus lambda times theta function. Now let's use this substitution. X is equal to cosine theta, which means dx over d theta is equal to minus sin theta. Now using this substitution, we can get a function of x from this differential equation, which becomes 1 over sin theta d dx sin theta d dx theta function dx over d theta, which is multiplied by dx over d theta, which is equal to minus lambda theta. So this equation becomes 1 over sin theta d dx minus sin squared theta d dx theta function multiplied by minus sin theta is equal to minus lambda theta function. This sin theta and this sin theta are cancelled out, and this sin squared theta is equal to minus 1 over cosine squared theta is equal to minus 1 minus x squared. Therefore, this equation becomes d dx 1 minus x squared times d theta over dx is equal to minus lambda theta, and this simplifies to 1 minus x squared, the second derivative of theta function with respect to x, minus 2x, the first derivative of theta function with respect to x, plus lambda theta function is equal to 0. As you can see, this is exactly the Legendre differential equation. Now I am going to write down the differential equation again using y. 1 minus x squared d squared y over dx squared minus 2x dy over dx plus lambda y is equal to 0. And the series solution that I am going to assume is y is equal to j is from 0 to infinity aj times xj. The first derivative becomes y prime is equal to j is from 0 to infinity j times aj times xj minus 1. Y double prime is equal to j is from 0 to infinity j times j minus 1 times aj xj minus 2. Now plug in these equations to this differential equation. I get 1 minus x squared times summation 0 to infinity j minus 1 aj xj minus 2 minus 2x summation j is from 0 to infinity aj xj minus 1 plus lambda times summation is from 0 to infinity aj xj is equal to 0. Now this summation simplifies to summation is from 0 to infinity j minus 1 times aj xj minus 2 minus summation j is from 0 to infinity aj times j minus 1 plus 2j minus lambda, everything multiplied by xj, which is equal to 0. When j is equal to 0 and j is equal to 1, this whole term becomes 0. So we can write this summation goes from j is equal to 2 to infinity j minus 1 aj xj minus 2. And now let's use another variable k, which is defined as k minus 2. When j is equal to 2, k is equal to 0, and when j is equal to infinity, k also goes to infinity, which means this summation can be written as k goes from 0 to infinity, and now j is equal to k plus 2. So k plus 2 times k plus 1 times k plus 2 multiplied by xk. Here k is just a dummy variable, so I can just substitute k by j again. Now I can write the full equation as summation j is from 0 to infinity j plus 2 times j plus 1 times j plus 2 minus aj times j plus 1 minus lambda. Everything is multiplied by xj is equal to 0. Okay. Now cosine theta is always greater than or equal to minus 1 and less than or equal to plus 1. Since x is equal to cosine theta, we are trying to find solutions where x is greater than or equal to minus 1 and less than or equal to plus 1. So within this range, so we have so many different values, actually infinite number of values, and for all these infinite number of values, this equation should be satisfied. Therefore, which means this term should be equal to 0. So we can write aj plus 2 is equal to j times j plus 1 times minus lambda divided by j plus 1 times j plus 2 multiplied by aj. And this is our recursion relation. Okay, now let's talk about the convergence of the series. To see the convergence, we need to consider aj plus 2 times xj plus 2 divided by aj times xj, which is equal to j plus 1 minus lambda divided by j plus 1 times j plus 2 multiplied by x squared. And we need to consider what happens when j goes to infinity. We can write down this as j goes to infinity 1 times 1 plus 1 over j minus lambda over j divided by 1 plus 1 over j multiplied by 1 plus 2 over j, and x magnitude is squared. So this becomes, since when j goes to infinity, this first term becomes just 1, and this becomes x magnitude is squared. When x magnitude is less than 1, we can say this is less than 1. When x magnitude is equal to 1, which means x is equal to plus or minus 1, we have this is equal to 1. Therefore, to make sure the series is convergence between all range of x values that we are interested, minus 1 to plus 1, we need to make sure that the series is terminated at some point, which means at some j value, j times j plus 1 is equal to lambda. So that value, that maximum j value, I am going to write as L. Lambda is equal to L times L plus 1. Now, this is a significant result because j is always greater than or equal to 0 and j is only an integer, which means lambda is always greater than or equal to 0, and also L is also greater than or equal to 0, and L can take only integer values from 0, 1, 2, likewise. Which means when we need to have a physically feasible solution for our Legendre ODE, we should have lambda in the form of L times L plus 1, and L should be an integer which is greater than or equal to 0. Now I am going to write down our recursion relation again. A j plus 2 is equal to j times j plus 1 minus L times L plus 1 divided by j plus 1 times j plus 2 multiplied by aj. Now let's first consider what happens when j is equal to 0, 2, 4 and values like this. When j is equal to 0, I get a2 is equal to minus L times L plus 1 divided by 1 times 2 times a0. When j is equal to 2, I get a4 is equal to 2 times 3 minus L times L plus 1 divided by 3 times 4 times A2, which is equal to 6 minus L plus 1 multiplied by minus L times L plus 1 divided by 4 factorial multiplied by A0. Now A6 becomes 4 times 5 minus L times L plus 1 divided by 5 times 6 times A4, which is equal to 20 minus L plus 1 times 6 minus L plus 1 times minus L plus 1 times A0 divided by 6 factorial. So as you can see, when j is equal to 0, 2, 4 and even values like that, we get a series of values which are dependent on A0. And let's see what happens when j is equal to 1, 3, 5 and values like that. When j is equal to 1, A3 is equal to 1 times 2 minus L times L plus 1 divided by 2 times 3 times A1. When j is equal to 3, A5 is equal to 3 times 4 minus L times L plus 1 divided by 4 times 5 multiplied by A3. Now this becomes 12 minus L plus 1 multiplied by 2 minus L plus 1 divided by 5 factorial multiplied by A1. Similar to that even number series was dependent on A0, odd number series is dependent on A1. Now let's consider what happens when L is even or L is odd. When L is an even number, we can find some j which is equal to L, so that j plus 1 minus L plus 1 is equal to 0. In that case, our even number series is terminating, so that series is converging. But our odd number series is going on and it is diverging. Therefore, we need to make sure when L is an even number, our odd number series also converge, which can be achieved by setting A1 is equal to 0. Similarly, when L is an odd number, we can find some j is equal to L, so that j times j plus 1 minus L times L plus 1 is equal to 0. Again, to make sure our even number series is not diverging, we are setting A0 is equal to 0, so that all the even numbered components are 0. Now let's observe the series for few different L values. When L is equal to 0, we are setting A1 is equal to 0 since L is an even value. Then A2 becomes 0 times A0, which is equal to 0, and after that A4, A6 and all the even number series components are also equal to 0 other than A0. Therefore, the series solution when L is equal to 0, which I am going to denote as P0 x, is equal to just A0. By selecting A0 as 1, P0 x is equal to 1. When L is equal to 1, lambda is equal to L times L plus 1, which is equal to 2. When observing A3, we can see A3 becomes 0 when L is equal to 1, which means A3 is equal to 0, A5 is equal to 0, and all the odd numbered values are equal to 0. And also when L is an odd value, I am setting a naught is equal to 0 to make sure that even numbered series is not diverging. Now the only non-zero component in the series is a1, and series becomes p1x, which is equal to a1 times x1. By selecting a1 as 1, p1x becomes just x. Now let's consider L is equal to 2 case. Then lambda is equal to 2 times 2 plus 1, which is equal to 6. And a2 is equal to, from this equation, minus 6a0 divided by 2, which is equal to minus 3a0. And a4 is equal to, from this equation we can see, since we have L plus 1 as 6, this term becomes 0, which means a4 is equal to 0 and a6, a8, all the even numbered components are equal to 0. And to make sure that odd numbered series is converging, we are selecting a1 is equal to 0 as well. Therefore, the solution when L is equal to 2 is a0 x0 plus a2 x squared, which is equal to minus 3a0 x squared plus a0, which is equal to minus a0 times 3x squared minus 1. Now after selecting a0 as minus 1/2, we can get p2x, which is equal to 1/2 3x squared minus 1. So why we selected our a0 and a1 constants like this way, that I am going to talk about in a future video. Likewise, we can get p3x is equal to 1/2 5x cubed minus 3x, and so on. But initially we tried to solve the differential equation with theta, and that equation was 1 minus sine theta d d theta sine theta d d theta. Theta function was equal to minus lambda times the theta function, and we proved that lambda should be in form of L times L plus 1, and L is an integer and L is greater than or equal to 0 to theta function to have a convergent solution, which means a physically feasible solution when this differential equation is appeared on physical systems like electromagnetics and so on. Since x is equal to cosine theta, our solutions for this equation become p0 cosine theta, which is equal to 1, p1 cosine theta, which is equal to cosine theta, p2 cosine theta is equal to 1/2 3 cosine squared theta minus 1, and so on. Therefore, whenever we encounter 1 over theta function sine theta d d theta sine theta d d theta theta function, we just say that it's equal to L times L plus 1, since we already know that theta function only have convergence properties when L is an integer as well as L is greater than or equal to 0. I will see you in another video in which I am going to describe what are the properties of Legendre polynomials and its orthogonality condition, and how it can be used to solve an example problem. Thank you.